This is question 2 of problem set 4. It's all about table-based problem solving for accelerated motion. In this case, a ball is shot straight upwards off the roof of a tall building with an initial velocity as given, and I also give you an acceleration. So here and here and here, these are all important initial values for the setup. So I've got an acceleration, an initial velocity, and an initial position. Those last two are new because in the last problem, those were both zeroed out. Let's get a really quick idea, a picture of this situation. So a tall building, ball is shot straight upwards, and then it's going to fall back down to the ground. So for a while, the ball's going to head upwards, eventually topping out somewhere, and then it's going to fall back down. So there's our sketch. I've already filled in the velocity column because I think by now you've had enough practice at it that makes sense. I have a negative acceleration and a positive initial velocity, so 40 meters per second plus a negative 10, 40, 30, 20, 10. You see how the velocities go in that column. Take a moment first and understand what's happening in the 4th second on this table. The velocity hits 0. Where is the ball at that moment in time? When is the velocity 0? Might be helpful to think about it as that the velocity is 0 when we reach the top of that flight. So that velocity is 0 here at the very peak. All right. That'll be relevant to us later on in the problem. Now let's take a moment and look at the position information. This is a bit more complicated because of the initial position being 100. But I need you to remember before we get going one important fact. The initial velocity is upwards, so the next couple of positions are going to be bigger than 100. It's going to go higher than 100 meters. So I've actually already solved it out. Let me just kind of reveal that. Okay, so let's take a look at how to figure out the positions. So this idea of just simply doing the area of the triangle, it's not going to work here because I've got a more complicated velocity situation. So I'm going to show you now a way to think about this. It's this backup method that I showed you in problem 1. So you get this second position here. I want to remember that if I take the average velocity times the time interval, I'll get how much displacement I have. So here we go. Average velocity times time. That's how far we travel. Okay, so first of all, from 0 to 1 second, my average velocity is 40 plus 30 divided by 2. That is between 0 and 1 second. That's a 1 second time interval. That'll get me in displacement. Let's see, 40 plus 30 divided by 2. That's 70 divided by 2, 35 meters. Okay. I'm going to displace 35 meters from where I started. So the position later on, the second position, is the initial position plus the displacement, right? So we're going to start at 100 meters and we're going to add 35 meters. And now we repeat this process over and over again. We'll do the second one together. So I've got, let's erase that so it's easier to see. I'm going to go back to the beginning of time. The average of 40 and 20 meters per second. And that is a 2-second time interval this time. And I'm going to go ahead and do this all in one step. It's the initial position plus that. I would recommend that you learn to do this all in one step on the calculator. So I'm going to do 100 plus parentheses. I get a position of 160 meters. So now my space is starting to get a little full. So we'll just do the next one. And then I'll let you calculate out the rest yourself. This time I get 175 meters. Now there's kind of two options you have from here. Number one, you could continue cranking out calculations. Yeah, it's going to take you a little time, but you know what you're doing at this point. Another way to look at it is to see if you notice any patterns in how these numbers are changing. 100 to 135, 135 to 160, and finally 160 to 175. I encourage you now, pause the video and work out the rest of these numbers. When you come back, I'll have them filled in for you. Welcome back. As you can see, I have now filled in the positions for you. Hopefully the pattern you notice is that initially there's a 35 meter difference, then a 25 meter difference, then 15, then 5. That's where we reach the apex of the journey, the highest up the ball reaches. And then we come down by 5, then we come down by 15, then 25, and so on. So there's a definite pattern in how the positions are changing. Hopefully, a big idea that you take away from this is this. The question later on asks you, look at part B at the bottom of the screen here. At what point in time will the ball reach the ground? How do you know? I want to invite you to study the position data to answer when the ball will hit the ground. So because the building is 100 meters tall, and we called that initial position 100 meters, that's 100 meters above the ground. So the ball reaches the ground when the height is 0 meters. And that's what I've answered here for part B already. This is about as complex as one of these problems can get. I have an initial velocity, I have an initial position, both of which are not 0. I have a negative acceleration. So make sure that you can do a problem like this and you've got the hardest possible version under your belt. Best of luck, and remember to consult the full solution guide.